This is a video from section 16.4 in a Calculus 3 class. The directions say to use Green's theorem to evaluate the integral over c of f dot dr. So make sure to check the orientation of the curve before you apply the theorem. So you want to make sure the curve is orienting in the counterclockwise direction. So if we take a look at number 13, we have the integral over c of 3 plus e to the x squared dx plus arctangent of y plus 3x squared dy. And I've drawn the curve below. And as you can see from the arrows, this curve is oriented in the counterclockwise direction, which is the correct direction that you want. Okay? Now, to apply this theorem, the first thing we need is m of xy and n of xy. Now, it's the same pattern as in the previous video. M of xy is going to be 3 plus e to the x squared. N of xy is going to be arctangent of y plus 3x squared. So the partial of m with respect to y is going to be 0 because x is constant. And the partial of n with respect to x, in this context, y is constant, so you're just left with 6x. So if I take the integral over c of 3 plus e to the x squared dx plus arctangent of y plus 3x squared dy, by Green's theorem, this is the double integral of. Now, remember x squared plus y squared is less than or equal to 4 and greater than or equal to 1. So we're going to integrate over that entire boundary here. And the integrand is the partial of n with respect to x, which is 6x, minus the partial of m with respect to y, which is 0, dA. And now we can transform this into polar. So I wait to set up the integral in rectangular, and from there I will convert to polar. I don't want to go to polar directly without going to rectangular first. Okay? Now, this is the double integral. Now, remember that x is r cosine theta. Okay? And so 6x is going to be 6r cosine theta. Now, dA, remember, is r dr d theta. That r is called the Jacobian. That's something you learned back in chapter 15. Now we need to get the limits on r and the limits on theta. On theta, theta is going from 0 up to pi over 2. All right? So let me rewrite that here. Think about the sweep. So if we go back to the picture, notice how we start along the x-axis, which is theta equals 0, basically, right? And we end along the y-axis, right? So we're going a quarter of the way around the circle. And that's why we're going from 0 up to pi over 2. And then my r is going to go from 1 up to 2. That's it. And so this is the integral from 0 to pi over 2. And then the integral from 1 to 2. of 6r squared cosine theta dr d theta. And so this is the integral from 0 to pi over 2 of 2r cubed cosine theta evaluated from r equals 1 to r equals 2 d theta. So you notice when I evaluate, I want to identify which variable I'm replacing these limits with. So here, I'm going to go the integral from 0 to pi over 2 of, replace r with 2. I'm going to get 16 cosine theta, right? 2 to the third is 8. 8 times 2 is 16. Replace r with 1, and I'm going to get 2 cosine theta. This whole thing d theta. So this is the integral from 0 to pi over 2 of 14 cosine theta d theta. But this is 14 sine theta evaluated from 0 up to pi over 2. Plug pi over 2 in for theta, and don't forget, sine of pi over 2 is equal to 1, and sine of 0 is equal to 0. And so here you get 14 sine pi over 2 minus 14 sine of 0. But I've already mentioned that sine of pi over 2 is 1, sine of 0 is 0. So the correct answer here for number 13 is, in fact, 14. If we take a look at number 15, suppose f of xy is equal to, the first component is y cosine x minus xy sine of x. The second component is xy plus x cosine x. And C is the triangle from 0, 0 to 0, 4 to 2, 0 back over to 0, 0. I strongly encourage you to draw a picture of that triangle because you have to make sure that the orientation is counterclockwise. And if it's not, I need to show you how to adjust for that. Now, here's the XY plane, okay? And we need to draw out C. So we're going to start at 0, 0. And then I'm going to travel up to 0, 4. And then I'm going to come over to 2, 0. And then I'm going to come back over to 0, 0. And so if I were to draw this triangle, this is what it looks like. I'll draw it in blue, like so. And I start at 0, 0. And I'm going up to 0, 4. And I'm going to go back down to 2, 0. And I'm going to go back over to 0, 0. Now, I don't know about you, but that looks like it's oriented clockwise. C is oriented clockwise. Now, we have to make sure that C is oriented counterclockwise. So we have to essentially make an adjustment. Now, C is oriented clockwise. But we do know that negative c is oriented counterclockwise. All right? And it turns out, if I take the integral over c of f dot dr and the integral over negative c of f dot dr, now, when you swap directions, remember c goes clockwise, negative c goes counterclockwise. They're going to produce opposite answers. Okay? Now, how do we make sure that they produce the same answer? If I put a negative out in front of this integral here on the right, it turns out these are going to give us the same value. So it turns out the integral over c of f dot dr is the same as negative the integral over negative c of f dot dr. These end up being the same thing I claim. Now, let's see if we can apply this here. Now, m of xy is equal to the first component, which is y cosine x minus xy sine of x. And n of xy is equal to xy plus x cosine x. Now, the partial of m with respect to y, that's going to be equal to cosine x minus x sine of x. Remember that the derivative of y is just 1. And if I take the partial of n with respect to x, okay, that's going to be y plus cosine x minus x sine of x. So that's just the product rule. So I took the derivative of x, I multiplied by cosine x, and then I said plus x times the derivative of cosine x, but the derivative of cosine x is negative sine x. And so that's where I get the partial of n with respect to x. Now, the integral over c of f dot dr. So once again, this is the integral over negative c of f dot dr. Okay? But there's a negative on the outside. And so this is negative the double integral. Now, I'm going to take the partial of n with respect to x, so that's y plus cosine x minus x sine of x. So over here, this is the partial of n with respect to x minus, now the partial of n with respect to y is cosine x minus x sine x. So let me write that down. And we'll integrate over d. We'll figure out what those limits are in a minute. So if you notice, so let me also add that this is the partial of m with respect to y. So the cosine x's go away, the x sine x's go away, and it just looks like we're taking the double integral over d with the negative on the outside of y dA. Now, we can figure out what our limits are. If we go back to the picture, remember this here is 0, 4, and this point here is 2, 0. The slope is negative 2, and so here y equals negative 2x plus 4. That's the equation of a line through the point 0, 4, and 2, 0. Now, think about where you enter and where you leave. So we could draw that over here if it's easier. So now we're integrating over a boundary, and it's everything inside that triangle. So here's 1, 2, 3, 4. Here's 0, 4. Here's 2, 0. And this is what we're going to integrate over. So it's that triangular boundary and everything inside. Okay? And let's not forget, the equation of that line through 0, 4, and 2, 0 is y equals negative 2x plus 4. So we're going to leave y equals negative 2x plus 4. So that's my upper y limit. And we're going to enter, remember, where do you enter, where do you leave? We're going to enter y equals 0. Okay? And then x is going to go from 0 to 2. 0 to 2. So it's a really slick way to do these limits. Where did you enter? I entered in through y equals 0. Where did you leave? Y equals negative 2x plus 4. And then x is going to go from 0 to 2. So x has to be, since the x limits are on the outside, you have to have numerical quantities. And so over here, this is negative. So I'm going to go 0 to negative 2x plus 4. And then from 0 to 2 of y dy dx. And so this is negative the integral from 0 to 2 of 1/2 y squared evaluated from y equals 0 to y equals negative 2x plus 4 dx, right? So I'm going to pull that 1/2 out in front. I'm going to integrate from 0 to 2 of negative 2x plus 4 squared dx. If it's easier for people to square that out, that's fine, if that's what we're going to see. So we're going to take negative 1/2 the integral from 0 to 2 of 4x squared minus 16x plus 16 dx. So this is negative 1/2 of, I get 4/3 x cubed minus 8x squared plus 16x, evaluated from 0 up to 2. So I'm going to plug 2 in for x, and I get negative 1/2 times 32 over 3 minus 32 plus 32. If I plug in 0, everything is 0. So the 32's cancel, and you're left with negative 16 over 3. And that's how you do number 15. If we take a look at number 18, suppose we have this. Suppose f of xy is, now the first component is square root of x squared plus 1. The second component is arctangent of x. And C is the triangle. From, we're going to go 0, 0 to 1, 1 to 0, 1 to 0, 0. So again, we need to draw this out. We have to make sure we're aware of what we're looking at, because we have to make sure that the orientation is counterclockwise. So I'm starting at the origin, and I'm going to travel out to 1, 1. And then I'm going to go from 1, 1 to 0, 1. And then I'm going to go back down to 0, 0. So you notice how I go from 0, 0 to 1, 1 to 0, 1 back to 0, 0. That orientation is counterclockwise. And that's a large part of why I picked that problem, because if you go back to the previous problem, this orientation happened to be clockwise. So we had to do a little manipulation to make sure that the orientation was in the counterclockwise direction. So we had to use this result for problem 15. We don't have to use that result for problem 18. So now, with that being said, let's come over here. M of xy is equal to, in this case, square root of x squared plus 1. And then n of xy is equal to arctangent of x. The partial of m with respect to y is 0. The partial of n with respect to x is 1 over 1 plus x squared. And so the integral over c of f dot dr. Now, whenever you're seeing a line integral and I say apply Green's theorem, you must set up a double integral. If you evaluate the line integral directly, you did not apply Green's theorem. That is one thing that can be confusing, but it's something that you want to be aware of. Now, we're going to set up our double integral. Now, the partial of n with respect to x is 1 over 1 plus x squared. The partial of m with respect to y is equal to 0. Now, we need to set up our limits. Now, we can try it this way, and I can show you what's going on. Think about, where did you enter, where did you leave? Okay, so I'm going to enter x equals 0, but I leave x equals y. So those are going to be my innermost limits. So I'm going to go from 0 to y. Okay, and these are x limits because where I enter and where I leave run parallel to the x-axis. So this is with respect to x. And then my y goes from 0 up to 1. Okay, now this is the integral from 0 to 1 of arctangent of x evaluated from x equals 0 to x equals y dy, like so. Now, when I plug in x equal y, so we'll do that on the next page. So I take the integral from 0 to 1 of arctangent of y minus arctangent of 0. And then I'm going to integrate that with respect to y. So this is the integral from 0 to 1 of arctangent of y dy. And so I'm going to come over here, and I'm going to let dv equal dy. Here, we'll do this one first. So we'll say it this way. It's classic integration by parts. We're going to let u be arctangent of y. So we'll do it in this order. dv is equal to dy. So du is 1 over 1 plus y squared dy. And v is equal to y. And so I'm going to take uv, which is equal to y arctangent of y, evaluated from 0 to 1 minus the integral from 0 to 1 of y over 1 plus y squared dy. Now, plug 1 in for y, and you're going to get arctangent of 1. And then the integral of y over 1 plus y squared dy, well, that's going to be 1/2 natural log of 1 plus y squared, evaluated from 0 up to 1. And if I plug 1 in for y, I get 1/2 natural log of 2. And if I plug 0 in for y, I get natural log of 1, which is 0. And remember that arctangent of 1 is pi over 4. So this is equal to pi over 4 minus 1/2 natural log of 2. And that's going to conclude this video for section 16.4. We worked problems 13, 15, and 18. Okay.